Throughout this lecture series, I've talked about how endurance running has played a central role in human evolution, and in particular I've argued that our unusual capacity for sustained locomotion, especially in hot environments, helped shape many of the anatomical, physiological and behavioural traits that distinguish us as a species. How our ability to hunt in the daytime heat on the African savanna gave us access to high-value calories, and how this energetic surplus likely contributed over many millennia to the expansion of our brains and eventually to the emergence of culture and civilization. I've discussed how, although we may not be the fastest of creatures, we're extraordinarily difficult to outlast. The peak running speed of the world's best human sprinters, around 10 meters per second, is far inferior to that of lions, which can reach speeds of roughly 30 meters per second, cheetahs, which can exceed 35 meters per second, and thoroughbred racehorses, which can sustain speeds of around 19 meters per second. But speed, of course, is only one dimension of performance. What sets humans apart isn't how fast we can run, but how long we can keep going. Elite endurance runners can sustain speeds of approximately 5.6 meters per second for more than 2 hours at a time, and when motivated, humans are capable of covering extraordinary distances over the course of a day. While other mammals may match or exceed us in specific ecological contexts, humans are among the most capable long-distance terrestrial movers, particularly in hot conditions. Some Kenyan marathon runners routinely run as much as 30 kilometers per day as part of their training, day after day, year after year. I also mentioned how our ability to endure has been predicated on a constellation of anatomical features. Long Achilles tendons that store and release elastic energy, large hips and gluteal muscles that stabilize the trunk during running, relatively narrow shoulders that permit efficient counter-rotation of the arms and torso, and maybe most importantly, an unparalleled capacity to dissipate heat through profuse sweating. Together, these traits make humans unusually well suited to sustained endurance exercise, especially environments where overheating limits the performance of other animals. The exploitation of these evolutionary niches may also have shaped other human characteristics, including mental and physical perseverance and a subconscious system of pacing and effort regulation. This system, sometimes described as anticipatory regulation, allows us, with appropriate pacing, to maintain effort for long enough to exhaust our quarry without exhausting ourselves. Rather than running until we collapse, we appear to regulate effort in advance based on experience, expectation, and physiological feedback. And it is the nature of how far or how long we can go before exhaustion occurs that I'll be talking about today. In the context of endurance performance, true exhaustion is ultimately determined by the balance between energy input and energy output, how many calories are consumed, and how many are expended during a given bout or series of bouts of physical activity. Even when you are sleeping, your body must spend energy to function. Your basal metabolic rate, or BMR, is the energy you use to maintain the most basic processes of life. Things like cellular maintenance and ion gradients, measured under highly controlled conditions in a near coma-like state. Your resting metabolic rate, or RMR, then includes all the chemical reactions going on in your body while you are awake but not physically active. Digesting the last meal you ate, maintaining posture, regulating body temperature, and supporting normal organ function. In everyday settings, RMR is usually the more practical measure and is typically about 10% higher than true BMR. So for example, an average-sized adult male weighing around 82 kilos might have a resting metabolic rate of approximately 70 calories per hour while sitting quietly in a chair. Based on this, if he did nothing but sit for 24 hours, his body would expend roughly 1,700 calories. When we consider total daily energy expenditure, which includes all the additional energy required for activities of daily living, this same individual might require about 1,000 extra calories, bringing his daily total to around 2,700 calories. That means nearly 2/3, around 63% of the energy he expends each day is devoted simply to maintaining his body at rest. And this appears to be true regardless of lifestyle. Whether you are a sedentary office worker in an industrialized nation or physically active hunter-gatherer, the proportion of energy devoted to basic maintenance is really similar. In a recent study using the doubly labeled water method, researchers examined members of the Hadza hunter-gatherer population in Tanzania. They found that after correcting for differences in body size and composition, the basal metabolic rates of Hadza men and women were no different from those of people living in Western industrialized societies. So to put some numbers on this, the average Hadza man weighed about 52 kilos and expended roughly 1,300 calories per day on basal metabolism, while the average Hadza woman weighed around 45 kilograms and expended about 1,060 calories per day. Because fat tissue is relatively metabolically inert, the researchers accounted for the fact that Hadza men and women have approximately 40% less body fat than the average Westerner. When they made this correction, they found that most adult humans expend around 30 calories per kilogram of fat-free mass each day simply to maintain their bodies, regardless of whether they spend the day sitting at a desk, manufacturing shoes, growing corn, or hunting and gathering. The upshot is that under normal circumstances, you spend more energy maintaining your body than you do on physical activity, even if you are highly active. Now, this can feel counterintuitive because the work of maintenance is largely invisible. Aside from the 15 to 20 gentle breaths you take each minute, there's little outward sign of the enormous metabolic effort required to keep you alive. But your heart is contracting around 60 times a minute to deliver oxygen and nutrients to every tissue. Your intestines are digesting your last meal. Your liver and kidneys are filtering and regulating your blood. Your fingernails are growing. Your brain is processing these words, and countless cells throughout your body are repairing damage, defending against infection, and maintaining internal balance. But what happens when you approach your physiological limits? How much energy can a human being actually expend in a single day? So this is often expressed as a multiple of basal metabolic rate and is referred to as metabolic scope. Clearly, it would be unethical to test this limit experimentally by deliberately pushing people into severe energy deficit. Until relatively recently, therefore, we didn't really know what the upper limits of sustained human energy expenditure might be, but we can learn a great deal from two specific contexts: ultra-endurance sport and extreme exploration. One of the most famous endurance events in the world is the Tour de France. The first tour, held in 1903, covered 2,428 kilometers and was won by Maurice Garand in 94 hours and 33 minutes, at an average speed of around 26 kilometers per hour. Over the decades, the route and distance of the race have changed, but today it typically covers around 3,500 kilometers, and the average speed of the peloton now exceeds 40 kilometers per hour. Because the energetic cost of cycling rises steeply with speed, largely because of aerodynamic drag, this increase reflects a substantial rise in the rate of energy expenditure required to complete the race. In 1988, researchers estimated that cyclists competing in the Tour de France expended, on average, around 8,000 calories per day, equivalent to around 4.7 times their basal metabolic rate. Over the course of the 21 stages of the race, that amounted to a total energy expenditure of roughly 168,000 calories. The success of the Tour de France inspired a North American entrepreneur, C.C. Pyle, to organize a similar event in the United States, but this time as a running race. The result was a transcontinental foot race from Los Angeles to New York, covering a distance of 4,960 kilometers. The first race began on Sunday, March 4th, 1928, and was completed in 84 stages, with an average stage distance of 59 kilometers. The winner of the inaugural race covered the distance in 573 hours, 4 minutes and 34 seconds at an average pace of 8.7 kilometers per hour. The return race was won by the runner-up from the first event, who completed the course in 525 hours, 57 minutes and 20 seconds at an average pace of 9.5 kilometers per hour. A reasonable calculation suggests that a 65-kilo runner moving at between 8.7 and 9.5 kilometers per hour on flat terrain would expend around 600 calories per hour. Spread across the day, this would correspond to roughly 4,300 calories per day, or about 2.5 times basal metabolic rate. Over the entire race, total energy expenditure would have approached 340,000 calories, around twice that of a modern Tour de France competitor. Now, as impressive as these performances are, they are arguably surpassed by the early explorers of the Antarctic. The British expedition led by Robert Falcon Scott man-hauled their supplies to the South Pole and back, covering around 1,400 kilometers to the pole in 86 days, followed by a further 1,082 kilometers over 73 days before frostbite and extreme exhaustion ultimately claimed Scott's life. Although direct measurements were not possible at the time, energy expenditure can be estimated using data from more recent expeditions. In the southern summer of 1985, Gareth Wood, Roger Swan and Roger Meir retraced the first half of Scott's 1911 journey, man-hauling all their supplies without support over 1,410 kilometers in 70 days. Doubly labelled water studies showed that their daily energy expenditure ranged between 6,000 and 6,900 calories, for a total of approximately 455,000 calories. These values closely resemble those measured in Dr. Michael Stroud and Sir Ranulph Fiennes during a 48-day expedition to the North Pole. Based on these data, Stroud later estimated that Scott's team may have sustained daily energy expenditures of between 5,900 and 6,900 calories for as long as 159 days, equating to a total energy expenditure of around 1 million calories. So what does all of this tell us about the limits of human endurance? A recent study comparing endurance events across a wide spectrum from marathons and ultramarathons to the Tour de France to a 140-day race across America found that metabolic scope decreases as event duration increases. For shorter events like an 11-hour triathlon or a 25-hour ultramarathon, metabolic scopes of 9.4 and 8.5 times basal metabolic rate were observed. During the Tour de France, which lasts around 23 days, this ceiling drops to around 4 to 5 times basal metabolic rate. Ultimately, for very long events like the 140-day race across America, there appears to be a sustained metabolic ceiling of around 2.5 times basal metabolic rate. This limit seems to be defined not by the harder lungs, but by the capacity of the digestive system to absorb and process enough energy to match expenditure. While the cardiovascular system can support energy fluxes exceeding 10 times basal metabolic rate for several hours, it can't do so indefinitely. Over long periods, the bottleneck becomes energy intake rather than energy delivery. When intake can't keep pace with expenditure, body mass declines, physiological systems are downregulated, and performance eventually deteriorates. Returning to the Antarctic explorers, this framework suggests that Scott and his team likely sustained metabolic scopes of around 3.8 times basal metabolic rate, well above what we now recognise as the long-term sustainable limit. In this sense, their deaths were driven primarily by a profound or prolonged energy deficit, compounded by extreme cold, injury, and environmental stress. Ultimately, survival and the limits of human endurance come down to energy availability. And with that, we reach the end of this lecture series, exploring the science of human endurance. Thanks very much for watching.